Uh-oh. This doesn't look good. I say that's definitely a problem with the mold here. And then this was the part. And you can see that chunk of metal should be right there, but it's stuck in the part. And then that's what the back looks like now. So definitely got an issue. I'm gonna have to fix this mold up. Had a little bit of a blowout. So this is one of the perils of using aluminum molds, is that aluminum fatigue fractures over time and can't hold up against high stresses like injection nozzles pushing on the back of a thin-walled aluminum block like that. Even though this was 70-75 aluminum, after 3,000 or 4,000 cycles of a few hundred pounds, or probably 600 or 700 pounds pushing on that, what used to be a chunk of metal, which is now in here, you wind up with stress fractures and your mold can break. This was basically a screwless part, you know, so that hole used to be the gate where these are normal parts that come off. So that little spot right there was the gate remnant, but the whole area where the nozzle was pushing on the backside of that thin section of the mold basically blew out. So we got to fix it. Thanks for watching Dragonfly Engineering. All right, I'm over here on the Haas TM1 mill, and I've loaded our damaged mold, the A-side mold, into the chuck, or into the vise. And what I'm going to do is use an indicator to sweep in the existing good portion of the machined hole that the nozzle for the molding machine poked through, and then blew out the cone shape of our aluminum insert, or our aluminum mold. So as I mentioned, since this area is so thin due to having basically the nozzle be the gate, the molding machine nozzle being the gate into the actual cavity of the mold, it was just too thin for the aluminum and it fatigued out. So my neighbor next door gave me this drop, which is off of his big CNC lathe, and this is 303 stainless, and it's about 1 3/4 inches in diameter. So what we're going to do is I'm going to make our repair insert out of this 303 stainless, and to do that I need to find the exact center and then machine out this busted out area of aluminum down to a depth of probably, oh, I don't know. Well, actually we'll just machine all the way through, and then on the back side of the mold we're going to machine in a step into this plug so that we can insert this insert from the back side of the mold, and then the face will be flush with our finished surface on the aluminum. So that's what we're going to do. I basically just need to minimize the diameter to clean up all of this blown out fractured cone on the mold itself. T7 ATC forward, and we're going to change our tool to tool number 7. Then I'm going to get the dial indicator and load it onto this tool, this Cat 40 tool holder, and then we can sweep in our hole. right, so we're out at the TM1 mill and we got the old floppy disk here. I'll stick it into the disk drive, go to list programs, and then, so this mill wants to see an O in the file name, so we have to say O and then 00099, F3 to read. And it says disk done, so we can go to menu and then we can see that this is the program that we just wrote with Mastercam. So let's run this circle pocket program and see what we get. So I'm going to slow everything down and hit cycle start and be ready on the cycle hold in case I see something I don't like. Again, I've got the feed at 50% and the pocket's starting from the outside, it looks like. We just want to make sure that we're not off or doing something stupid. We're helixing in. And now we're doing the actual center of the cut. And we just cleaned up that broken edge there, so that's good. Yeah, I think we're centered pretty good and we're cutting away our busted cone. I'll see that a little bit. Get you a better angle. All right, so looking at our pocket that we made here, this was basically a test pocket to find where the farthest extent of the fracture occurred. So we got a nice clean pocket here. So now what I'm going to do is go back to Mastercam and program this pocket to go all the way through to the backside clearance of this mold block. And that will be our new plug. And then from the backside, we're going to have to flip this mold over and then machine a flange key or a flange ring so that our new stainless insert can't push all the way through the mold as well. And then we'll have a good inch of aluminum or about 25 millimeters of aluminum. Well, actually after the flange, it'll probably be a 3/4 of an inch of an aluminum ring and supporting flange that will prevent the new stainless plug from doing what the thin aluminum billet portion did and which broke out. So I don't think there's going to be, I don't know, an order of magnitude more support on this insert that we're going to stick in here than what was originally there. So I will be right back and program the same program to cut all the way through. Okay, so we are ready to do our final cut all the way through. So I got the program loaded and the tool and everything, and the zero's already set, so I'll just hit cycle start. I made the cut a little simpler this time, not so many passes, because we already know that we've got a good geometry. I'll start the coolant this time. Now we're doing the finish cut. Yeah, Mastercam is a little smarter than my 15-year-old visual mill toolpath program in that it understands stock clearance a little better, so it didn't actually pull all the way out to a clearance plane to do the finish cut. And we are done. So while the TM1 is doing its spring pass, we can load our 303 stainless into the, what is this, the Track TRL 1630 CNC lathe from Prototrack. Not sponsored, of course. Okay, so we'll open our jaw. This is a 3-jaw chuck. I think we only have one critical setup, so we can get away with doing a 3-jaw. We'll load our 303 stainless plug in here. I might have to clean up some of the remnant from the last cut. Again, this was donated by my neighbor. All right, we'll clean up this face. Yeah, it looks like it was a little out of round on that final cut there from the previous user. Maybe not, maybe it's just me chucking it funky. Well, we'll face it off. I think this tool is kind of dull. Well, actually, it's all right. I think it just had some aluminum remnants on it. I'm just manually turning the encoder wheels. So basically running this like a manual lathe. All right, so I'm going to tell the mill that this is a 50 millimeter diameter. Oh, it already basically is set to that. That's cool. And Z absolute. Spindle speed, we will say surface feet per minute of 100. And absolute set. And then we'll take 0.2 millimeters off. You can see a nice little red cherry. And theoretically, that'll be the right temperature every time. And then I'll drag the cut back out to help spring pass it. You hear the spindle slowing down to keep a constant surface rate, or surface feed. There we go. Our Z was set when we faced off the front. We're going in about 19 millimeters. I'm still manually turning this with the encoders on the CNC lathe. So they were at 18. I think maybe I will change this bit. No, it's not bad. If I do a backward spring pass, it cleans up pretty good. Alrighty. Shut off that spindle. Excuse the air traffic. Absolute. Okay. Now we can turn down some of the material. I may have to turn on coolant since this is stainless. Yeah, I get a little hot spot there. Alrighty, I'm gonna get the shroud on and turn this with coolant. You may not be able to see much. Alright, I gotta bust these, or knock these two guide pins out so that I can clamp across both vices. Since we're going to do round machining, I don't have to dial this vise in perfectly, but it does have to be sitting on the table with no obstructions under it. I might just slide it into place. All right. We'll slap our mold on upside down. Now we need to repeat the process and find the new machine circle that we cut when we were on the backside. So I will do that now. And it has to be our new machine circle, not the residual clearance circle that we originally had in there, so that we can kind of lock in our concentricity of our two operations. Who is he going to reach? I don't know if I can reach the lowest machined hole. All right, I got the needle on 0 on this side. And not over there. And a little over 15. All right, we're good. All right, so looking in the backside of the mold, so this big notch right here and this notch here are clearance pockets for the electrical housing for the heater, the nozzle heater. There's like a sheet metal box with wires that come in, and we need to clear that box. But looking down here at the bottom, there already is a machined pocket or a ledge there, and this ledge, or this OD of this small ledge, is actually slightly bigger than the core stock that I have for the stainless steel plug that my neighbor gave me the other day. So it could be that I actually don't have to machine anything back here, but I just need to basically find the thickness of this machined operation we did in the inner hole there that we did in the previous operation, and just let the stock rest with a flange on this edge right here, and then I'll just have a little bit of clearance. And I may actually be able to, well, I'm going to shoot for pressing this stainless steel core into this machined hole that we did on the backside. So I may have just wasted some time by flipping this over and finding the center, but it's also good to have a good work surface when we're going to actually insert the stainless core. And I'll be able to measure a little better from the backside here. So maybe a little waste of time, but maybe not, who knows. All right, let's get back to the stainless steel lathe operations. Okay, so I'm gonna find the depth of our machined pocket from the other side by putting this piece of soft aluminum up against the bottom, or the face of the mold, and then I'll plunge measure with this caliper. .55, and then this telescoping gauge I just put into our hole that we need to match, and this dimension, this is a telescope gauge, is 41.97. So I was 1/1000ths undersized on that hole. That's good to know. But we want to have a slight press fit. It's a little tricky to, you need to have this pass right through. So 41.98, but that's a little loose. 41.97. Okay. So we want this to be 41.99, I'm thinking. And that'll be a 0.5 thousandths or 10 micron difference. Okay. So let's do that. Yeah. All right, I'm going to measure this. All right, so now we're going to drill in our new sprue hole. This is going to be a really short sprue, ideally with an angle on it, because this is the mold surface now. Let me get this out of there. So we'll do a center drill to spot the location. And I'll switch this out for a 100 thousandths or 2.5 millimeter drill bit. We want the sprue to be small so it breaks off with very little residuals on the part, but not so small that it screws up the injection profile of the plastic. All right, here we go. Could probably speed this up some more. All right. And now I'm going to taper this hole a little bit so that we have a tendency for the plastic to break off close to the nozzle. So got a tapered square end mill here, and we're going to use it as a drill, or more like a tapered reamer. And we're going to turn this slowly, because a lot of times end mills like to chatter in holes. Okay, here we go. I'm just hand cranking the tailstock. I'm just going to get a little bit of an edge break there. There we go. All right. And that is it. All right, so we'll cut the back off on the bandsaw and then finish or square up the back and then drill our clearance hole for the injection molding nozzle to go through up to about where my finger is. Okay, we're back from the bandsaw, so we'll stick this part in our chuck so we can access the backside. And I'm just gonna face this off clean. We're gonna hollow out a big round pocket for the injection molding machine nozzle to fit in. And then with a 1-inch ball end mill, we're gonna radius the inside for the seat for the nozzle for the molding machine, which is a 1-inch hemispherical tip with a hole in the middle for the hot plastic to flow through. Probably should do the coolant again. This dimension isn't too critical either. Should speed it up though. Oh, we can do the surface feet per minute. That's always fun. Say 100 surface feet per minute. All right, so I'm going to do a edge chamfer. I actually did it, but the camera wasn't running, but I can show you again. So I'm going to go to the controller and click on do 1 and then taper 45. Now when I turn this knob, we will cut a 45-degree edge break onto that. And the lathe basically calculates the 45-degree angle and changes X and Y to do that. It may be hard for you to see. Anyway, so that's the edge break. All right. So we can drill out up with a bigger pilot hole. And this is clearing out the web in the middle of the next drill bit, which may be this one. So I think we'll try this drill bit next. Maybe too big. And be real careful with this cut. Give it some lube. In fact, I should probably double check that I got a good pinch on the part.
Want to hear the most annoying sound in the world? Guys!
All right, so I had to actually go to the tool store and scrap some adapters and things together to get this half-inch ball end mill to fit into the tailstock of this lathe. So to start, I've got this ER40 collet right here, and the half-inch end mill with a 3/4 inch shank fits into that. And then this guy goes into this collet holder to Morris Taper 3 adapter for a lathe that I used to have. So we'll screw on our ER40 to Morris Taper 3 adapter. I'm probably not doing that right. With these collets, there's always a trick. So this one, you got to snap into the nut first, like that. And the nut retains it. And I think the nut is actually the precision alignment, so that this is free in there. And then we stick our 1-inch ball end mill into the 3/4 inch collet like so. I'll tighten all this off camera. And then I had to get a Morris Taper 3 to a Morris Taper 4 adapter, which is this thing. And they put a slot in here to kick out the Morris Taper 3. So I will jam these together. I've already cleaned them. So basically if you just push these two tapers together, then it locks pretty good. And then this will fit into the tailstock of the lathe. You were off camera, so let's back up the spindle. And it kicks out our Morris Taper 4, like so. And I will advance the spindles out of beyond the eject position, I guess is for lack of a better word. And then we'll stick that guy right in there. And now that taper is locked, and I just need to get a spanner to tighten down our end mill. Tighten down this nut. I don't have a torque wrench or anything, but this was kind of quick prototyping. We'll bring in our 1/2-inch end mill, our 1-inch end mill with a 1-inch radius, our 1-inch end mill with a 1-inch diameter or 1/2-inch radius. And I'm going to give it a little WD. And then we'll slowly bring this guy in and see what happens. It shouldn't be as rough as that drill was. Yeah, that sounds pretty good. Yeah, this machine is not super rigid for these big tools. And we got 2 cutting surfaces, so that makes more chatter than a single point cutting. Okay. That may have done it. It's a little tricky to measure in there. But yeah, here's our new nozzle interface. And I'm gonna do some eyeball measuring. All right. So this is an inside diameter, so we're gonna have to tell it to do an edge break or a chamfer with a minus 45-degree angle. So I'll go to, on the screen, do one, taper, minus 45. And then if everything goes as planned, we should cut an inside chamfer here. Yeah. At a 45-degree angle. Here we go. Definitely have a lot of flex in this cheap tool. It's a dull, cheap tool. All right, I think we're done. We'll back out of there. I may hit that with sandpaper or something because it's not beautiful. Because we don't want to have sharp edges in here that grab molten plastic and have blobs solidify into like serrated grooves and things, but this doesn't look great at all. But what are you going to do? Okay, here is our part. Look at our stainless steel nozzle insert fix for our mold. So now I'm going to have to surface finish or bead blast this side, and it's going to push into the mold from the back. So we've got the A side of the mold sitting face down on a hot plate, which maybe is out of view, but I've got this mold up to maybe about 200 degrees Fahrenheit or 100 C. Oh, actually it could probably use some more heat, but I don't want to get it too hot and start messing up the O-rings that are inside of the mold. So, but what we're going to do is we're going to cool our insert with a cup of ice. And we're going to heat up our body, our aluminum mold block, with a kind of a dorm style hot plate for cooking. And I am going to spray a little lubrication into our hole. You can see it's warmer at the bottom because we got a little smoke coming out from our WD-40 interacting with the aluminum. So maybe I will turn the heat off. It's been sitting here for a while, just soaking in heat. And now I've got the plastic dowel to help drive this part in. I'm going to try not to burn my fingers by starting the part in the hot pocket. All right, now I'm going to try to hammer it home. And it went right in. Great. So we got the half thousandths, or the 10 micron difference, or the interference was handled by heating up our mold block and cooling off our insert. And it dropped right in with basically no problem. That's some of the water boiling off on this hot plate. So maybe I'll pick up our mold. And see how we're looking. It is recessed a little bit, but I think when the molding machine presses in, everything will find its home. And now it's standing up a little. It's hard to tell because I left the burr on both parts. I feel a burr from both directions. And I'm going to bead blast this. So basically the bead blasting is going to push this aluminum burr into whatever gap I've created there. but that should be good enough for this product because it's the back view. But I think bead blasting will definitely help blend everything together. So let's set up to do some bead blasting next door. Alright, I think we're looking good here. Decent production flow so far. Let's see how we look. Here it is. Saved the day with the stainless steel plug. Thanks for watching Dragonfly Engineering. See you next week.